Okay, thanks. White chalk should be somewhere. Okay, so I want to talk about some joint work with Boaz Barak, Zeev, Dvir, and Amir Yehudayoff. And it's all extremely elementary, basically about points and lines in space. So I'll explain everything and I'll prove essentially everything. The starting point, so I will not mention during the talk the motivations that got us to work on it, but I'll write them down maybe on the side so that you can ask at the end. So some of it has to do with matrix rigidity. Some of them have to do with locally correctable codes. And it's related to various questions in additive combinatorics. And I don't think I'll get to mention them, but we can see at the very end. So the first thing I want to start with is a basic problem that we are going to, basic result that we are going to generalize, and this is well known under the name the Sylvester-Galai theorem. It's actually not quite a theorem of Sylvester and Galai. I guess it was conjectured by Sylvester, and it was also conjectured by Erdős. So these guys actually conjectured it independently. And then Galai and also independently Melchior proved it. So it's really their theorem, but people know it as the Sylvester-Galai theorem, and it says the following. Suppose I give you, we are in some maybe high-dimensional space. Most of the talk I'll talk about the real field, but you can, well, sometimes we will talk about other fields. And in it, we have a set of points, a finite set of points P. So it's some finite set of points, let's say of n points in this space. For what I'm going to say now, you can really even think about the plane. And suppose I tell you that they have the following peculiar properties. So here are the points. And suppose I tell you that no matter how I take a line through any pair of these points, I hit another point. Well, you see, I'm adding points so that the property holds, but you know, I try these 2 points, and there is a third point here, and so on. So what we are assuming is the Sylvester-Galai theorem. If every line through 2 points in P goes through a third point. So how can such a collection of points look like? Can anybody give me an example?
3 points on a line.
But we have many points. 100 points.
Well,
yeah.
for n equals 3.
Well, it's actually your answer is good also for n equals 100. So right. So here's one example. If all the 100 points are on a line, then it certainly satisfies this condition. So can you think of a different example? No. Good. Okay. If you read the abstract, then it's cheating. So what this implies is that all points are on one line. So this is the only way this can happen, this peculiar situation. That's the only way it can happen. And we are going to generalize this in several ways, but what I want to show you first is the proof of this theorem, because it's like a one-line or one-picture proof. It's really beautiful, and in some sense it's non-trivial, at least in the sense that these two guys who were, pretty smart, couldn't do it. And I don't know, this problem has a history of people publishing. So there is sort of a note of Sylvester called problem number 11,591, which is this problem that appeared in an article in a journal called Educational Times, where he poses this problem. Anyway, what's the proof of this? So here's the proof. So suppose not. Suppose not. So not all points are on a line. So now we can look at all lines and all points. And for whenever we have a line L and some, so lines, I mean just lines through pairs of points of this set. Okay, so we have some lines, and we have some point which is not on this line. We can look at the distance between L and P, right? It's well defined. And since we have a finite number of points, this set of distances is finite, so it attains some minimum somewhere. So there is some line somewhere and some point. So this is L and this is P, for which this distance is minimal. Okay, now we are going to arrive at the contradiction by providing another line and another point that attain an even smaller distance. Okay, so how are we going to do that? Well, this line has 3 points on it from our set, right? So at least 2 of them are on one side of this. So let's say the points are here. Right, these 3 points also from our set. Well, in this case, if we look at this line, obviously this distance is shorter. Right. Okay, so that's the proof. So what do we want to do with it? We are going to want to just make quantitative analogs of this. So in this theorem, the condition is very strong. It says that every line through every pair of points, you find another point on that line. So let me make up notation. Let me say that a line L is special if it contains at least 3 points from this set. Okay. So in this configuration, the assumption here is that all lines are special. Every line contains at least 3 points. So what we are going to want to do is relax this condition and say, well, suppose only some of the line, many of the lines contain 3 points, are special. And it turns out that you have to think about it a little bit, but just saying a constant fraction of the lines containing 3 points is somehow not the right generalization. So here is a right generalization, and that's the theorem I want to prove to you. So let me beforehand, maybe I'll just make up notation, or maybe we'll even give a name to it. So what is the delta, let's say, Sylvester-Galai configuration? So P, the set of points, is a delta, where delta is some number between 0 and 1. When is the set of points in a delta Sylvester-Galai configuration? If for every point, the lines through P cover a constant fraction, a delta fraction of all the other points. Okay, so the special lines, sorry, special lines for P cover at least delta endpoints. Okay, so this is true for every point. So maybe delta is 99%. So for every point, if you look at the special lines, lines containing at least 3 points, through P contain 99% of the points. So this condition is met approximately, or maybe delta is just 1%. So special lines through P, through every P, contain just 1% of all the points. So actually, can you give me an example of 1% Sylvester-Galai configuration? Which is not one line. 100 lines. 100 lines, yeah, 100 lines. So if we took 1 over delta lines, and we put about delta fraction of the points on each, then we get such a configuration. So certainly, this theorem doesn't hold anymore. I mean, these lines can be in, at least in something like dimension 2 over delta. So if they are in general position. So, is this everything? Is a small number of lines everything, or are there other? You think of another configuration in which every point participates in lots of. If the special lines through every point go through most of the other points, or 1% of the other points. So this is one example. And another example is, for example, take a grid. Suppose the points are on square root n by square root n grid. Then you can see that at least if you pass lines through a point with neighboring, with points in some constant fraction of this grid next to them, let's say this guy and this guy, this will meet, I guess, a third point here. So that's another example, which is very different than having just few lines. Here there are lots of lines, lots of different lines, but nevertheless, special lines through every point cover a constant fraction of all the points. So what is the right generalization of the theorem? Is there a structure that we can infer from this condition? Yeah.
Can you make it so you just hit 3 points and no more than 10 on the grid?
You mean if I went like this?
Yeah.
But I'm looking at all special lines through the point. Yeah.
Points that every special line through. Okay.
So for every point, if I look at all lines through it which contain at least 3 points, they hit a constant fraction of all the points. Yeah, so that's another example. And the theorem is that basically these are the only examples. So the theorem is that the structure is all the points have to live in constant dimensional space, has to live in very small space. So if P is delta SG configuration, implies that the dimension of P is at most some fixed constant over delta squared. So they have to lie in a constant dimensional space. Doesn't matter how many points there were. And this was, so this is what we proved, and very recently, Shubangi Saraf just tightened this to the absolute minimum, which is a constant times delta. So it actually, these points have to live in a 1 over delta dimensional space, and that's the best you can hope for up to the constant because of this, construction of just taking 1 over delta lines in general position. So I want to prove to you this theorem, and so the statement is clear. This proof is actually a combination of a bunch of simple things, but the simple things come from various places, some combinatorial, some algebraic, and some kind of analytic. And I want to explain these parts, and I think they're really neat. So that they combine so well and that they are so simple. So let me start explaining why. Yeah. So how do we even attack this? So yeah. Yeah. For this thing, it's about 13. I think here it's a little larger. It's not a crazy constant. It's in the tens and probably can be tightened. But it's independent of D. It's independent of, yeah, D doesn't play a role here. I mean, you can take D to be infinity initially. Okay, so good. But it's a good question about this constant because it certainly doesn't, Sylvester-Galai theorem is not a special case of this. We don't recover the constant one. I should perhaps say here that in the paper we prove several other theorems. So this generalizes Sylvester-Galai theorem. There are other results on incidences in the combinatorial geometry literature, and for some of these, we also have quantitative analogs, and I'll just mention one result, which, well, maybe first the Motzkin-Rabin theorem, at least for those who know. Is this about colored points? So it's some generalization of Sylvester-Galai where the points are colored, and you can prove quantitative analogs. And another is the Hansen and Bonis and Edelstein results, which talk about not incidence between points and lines, but between points and flats in higher, k-dimensional flats for some k. So let's say points and planes or points. And these are results of very much the same nature as Sylvester-Galai. All the incidences happen, if there is a universal quantifier, then you get a precise structure, and we can prove generalizations in which you have a quantitative analog if, it doesn't happen for all, but for 1%, and you get similar results. But I will not talk about this here. I want to explain.
Is there a lower bound on the constant? Do you know?
I don't know. It's a good question. I don't know. Better than one. Well, two. Sorry, 2 is certainly, yeah. Yeah, that's the best I know. So how are we going to get a proof? So think about this set of points. So we are in RD. So let's just write every point. So here are the points, this n points. And let's just write their coordinates. So let's just write the points down. So this is P1, P2 up to Pn. So we write a matrix of just the coordinates of these points in d-dimensional space. Doesn't matter. We fix the basis and we write it down. And what do we want to prove? We want to prove that the rank of this set, of this matrix, maybe that's called the matrix P also, not using notation. We want to prove that this is small. Well, let's call it something. Well, something small. So how can we prove this? It's not clear, but certainly one way to do it is to do the following. Let's look at what does it mean that 3 points are on a line. So this is, I don't know, P1, P2, and P3. What it means is that there is an affine relation between them, right? There are constants alpha, beta, and gamma, so that alpha P1 plus beta P2 plus gamma P3 is 0. right? So let's write these linear relations here in another matrix. So this was n, I guess, so this is n. And here we write a big matrix, let me call it m prime, where we write, for example, alpha, beta, and gamma.
Add an all one vector or something to the right.
You can add an all one vector to the right, so it'll be fine. Okay, so we write, we had a relation between P1, P2, and P3. We can write alpha, beta, gamma here corresponding to P1, P2, and P3, and zeros everywhere else. So when we multiply this row by this matrix, we get a 0 right? We get a 0. Okay, then we can take another relation. There is some other, line here, and we can get another one, maybe alpha prime, I don't know, beta prime, gamma prime, and a double prime. So let's just take all the special lines that we have, all the special lines, and for each one we write the linear relation, and we keep getting zeros when we multiply this matrix by this one, right? So when we write down all linear relations here, we get the 0. So when we have the product of two matrices is a 0 matrix, one way to prove that the rank here is small is to prove that the rank here is big, right? I mean, because they are orthogonal. So it would suffice to prove that the rank of this m prime, so we want something like this, so it will suffice that to prove that this is at least n minus c. So c is what we are shooting for, is 1 over delta squared or something like this, right? So it suffices to prove that the rank of this matrix is small. So the way we are going to prove, so this will be really the main thing, to prove that the rank of this matrix, of the linear relations, is nearly full. So what do we know about this matrix? We certainly don't know much. I mean, so here, let's collect the things we know. We know about m prime. We know that in every row we have at most 3 points, 3 non-zeros. Okay, so we are going to look at the zero non-zero structure of m, and from it we are going to infer the lower bound on the rank. So, in m prime, we have the following. At most, let me call it q, which will be, in our case, 3 non-zeros. So let me write it like this, and I'll just use nz. So we have at most 3 non-zeros per row. That's one thing we have. The second thing we know is that every, we know that there are lots of points on the special lines. So when we look at P1, we look at how many relations it participated in. How many do we have? Through every point, the special lines covered at least delta n other points. So we should have at least delta n non-zeros in this column, right? And similar for every column. So this is at most per row. Second is that at least, and let me call it k, which will equal delta n in our case, at least k non-zeros per column. Okay, so these are two conditions that we have on this matrix M prime, and they are not sufficient to prove a rank lower bound. It's very easy to give counter examples. And so we need an extra condition, and in order to do this, we are going to prune M prime. We are just going to select some of the rows in a matrix M. So we actually will look, what the matrix we will look at is a matrix M, which is just some subset of M prime's rows. So I'm just going to throw away some rows from M, so that I'll have a third condition. And this third condition will hold in. So we are going to make sure that these two conditions hold only in M. And on top of it, the third condition will say that when you look at two columns, so here when you look at, so we'll still have, very few, these are the non-zeros. When we look at two different columns, they will have very few non-zeros in common. There will be like somehow a design, a combinatorial design. So the third condition is that every two columns, so this is per row, per column, and now every two columns share at most some small constant, so let me call it t. In our case, t will also be something like 3. Share at most t non-zeros. Okay, so again, we look only at the zero non-zero pattern of this matrix, and what we demand of M, which is a subset of M prime, is just for every two columns, we have very few, some small number of non-zeros in common, rows in which they share non-zeros. Okay? So the third condition, I mean, the first two were given to us. The third condition we have to generate, and M we have to generate. So let me mention briefly how to do this, and then proceed to show that matrices like this always have high rank, very, very high rank which is nearly full. Okay, so how can we have large intersection between two columns? These are all the special lines going through one point, and all the special lines, points on special lines through P2, from P1 and P2. And it's pretty clear that one source of trouble is lines that have many points. So here, if we have here P1, and here we have P2, and here we have many other points, in this matrix M prime, we took this triple, and we took this triple, and we took this triple, and therefore we had, there were a big intersection between the non-zeros in column 1 and column 2. And the obvious solution is not to take, on lines which have many points, not to take all triples. Okay, so every row here corresponded to a triple. Not to take all triple, but to take what's called a design. So if we have here R points, without loss of generality. So the rows we will take from here, so take a set of triples such that every pair at most in exactly, let's say, one triple. So this is called the combinatorial design. So take only triples, take a set of triples so that every pair participates in exactly one. For some values of R, you may not be able to do it, but then if you have one less point or one more point, you can do it. So let's just assume that such a set of triples exists. If you've never seen this kind of things, there are many constructions of such sets of triples. For example, if you took all the three-term arithmetic progressions, okay, arithmetic progressions not of these points, but just of the set, in the set 1, 2, 3, up to R. If you just took all three terms arithmetic progressions, then you get such a set of triples. So that's one way to do it. And if you take this subset of rows, you get a set of rows which satisfies this condition. So you get, you just take these triples, and on the one hand, more or less by definition, the number of collisions here will be 1 or 3, depending how you count. But anyway, a small number of non-zeros common to every set of columns. And on the other hand, we didn't lose in the length of these columns in having many non-zeros per column, because if we take such a complete set of triples, for every point was taken from every line it participated in r times. So altogether, the number of non-zeros we count per point will be over all the special lines it participated in, delta n as before. Maybe we lose a factor of 2 there, but this is not going to matter. So anyway, that's a very high level or sort of hand-wavy explanation of how we get into this situation. So I want to now solve questions about this. So I want to sort of capture what we, where we stand. So we have what we call, so M is a, I want to call it a K QT design matrix. So it has these 3 properties. And again, these properties depend just on the zero non-zero pattern of this matrix. Every column has k points, every row at least k points. Every row has at most q non-zeros. So non-zeros, non-zeros, and every 2 columns share at most t non-zeros. So that's a design matrix. And the main lemma is that every such matrix, no matter what values appear in the non-zero locations, has a very high rank. So rank of M is at least n minus n q t over k squared. Okay, so again, every matrix like this must have high rank high, which is almost n, the number of columns. It's almost maximal up to this. And you can see that in the parameters we are talking about, this is a constant. So these 2 are absolute constants. And n over k is 1 over delta. So we get back the theorem that I erased, the main theorem that I erased, right? We are proving a lower bound on the rank of M, which is suddenly a lower bound on the rank of M prime, and therefore we get this upper bound. So this is the main lemma. So that's what I want to prove. Now, how do you prove it? So this is obviously a lower bound on an infinite family of matrices. The entries here can be, anything. Integers, rationals, big, small, whatever you want. So how do we prove a lower bound on this? And somehow the conceptual trick is to make believe that we understand the entries of this matrix. And what better understanding can we have? So let's say do a toy example. Toy example is that to assume, to make believe that all non-zeros are actually 1. So it's a 0, 1 matrix. Let's assume it's a 0, 1 matrix, see what we can prove, and then worry about the general case where it's not a 0, 1 matrix, but some arbitrary crazy matrix. I should mention that proving lower bounds on the ranks of matrices which depend only on the zero non-zero structure is sort of a big area and has motivations in various fields, in game theory, some optimization, and other places. People are interested in proving lower bounds on ranks where you know only the zero non-zero pattern of the entries, or you know only the sign pattern. And so that, you can think of this main lemma as belonging to this area. Okay, so let's do the toy example. The toy example, again, is that all non-zeros are 1. So you just have 0, 1 matrix over the reals with entries that look just like that. So few entries per row, many entries per column, and small intersection between the columns. and all non-zeros are 1. So why is this an easy case? Why is this? And the reason it's easy, so is a very simple spectral argument, algebraic, spectral argument, which I'll do for you. It's sort of 2 lines, which I'll do for you. So this somehow here comes, at least for this 2 example, comes an algebraic argument. We've done the combinatorial argument, which we just saw was pruning m prime to m via these designs, these triple systems. And now this is the algebraic part. And then the end will be just this. To convert this 2 example to the general case will require some analytic trick or analytic insight. So we have this 0-1 matrix, and we want to understand it. So here is a matrix. Again, M, and let's do the following. Which direction do I want to do it in? To multiply the columns. So let's multiply M and M transpose. So we multiply it, and we get some square matrix, n by n matrix, which we are going to call A. Okay. So what we are actually going to do is actually prove that the rank of A is large, minus what we want. And since the rank of A cannot be bigger than the rank of M, it suffices, right? So we'll prove a lower bound on the rank of A. Now the rank of A, what do we know about it? So let's look at how A looks like. So what are the, so this is A. If we look at Aij, the entry, any entry here, what do we know? So the diagonal entries are the inner product of, of a column with itself. And it's a 0-1 column. Right? So and it has at least k ones. So every diagonal entry here is at least k. Right? On the other hand, every 2 columns intersecting at most t positions, against these positions are 1s. So off diagonal, so these are at least k, and off diagonals, Aij, are at most t. So these guys are at most t. Right? I is different than j. Are at most t. So you look at this, and k's are, these are really big. They are like delta n, and t are really small. They are constants. They are 2 or 3. Right? So basically, you at least staring at it like this, it looks like almost an identity matrix, right? A very big diagonal, almost negligible off-diagonal entries. It looks like an identity matrix should have the rank of an identity matrix. How do you prove it? Well, let me prove it. And this is a spectral argument here. But let me simplify my life and assume that these are exactly k. Okay? It's no loss of generality. Anybody sees why? Yeah, I can scale. I can just multiply every column by, sort of by a number that will make this k and will only make everything else smaller in the column. And we'll come back to scaling soon. So anyway, it's no loss of generality to assume that the matrix looks like this. We want to show that its rank is high. So what do? Let's look at this trace of the matrix A squared. Okay? Take the trace and square it. Well, the trace is exactly k times n, right? So here we have k squared, n squared. On the other hand, the trace of the matrix is the sum of its eigenvalues. So if we think of, so the eigenvalues of A are lambda 1, lambda 2. Then this is equal to the sum of lambda I squared. And here comes a really critical thing. We want to use Cauchy-Schwarz. That's sort of obvious. If we want to prove an inequality, we have to use Cauchy-Schwarz somewhere, almost. But the key thing is that we want a bound on the rank And it's really important at this point to say, look, if the rank is R, then there are only R non-zero eigenvalues, right? There are only R non-zero. So we are going to take this sum only from 1 to R, and this will be critical in the, we apply Cauchy-Schwarz with this R. So this is at most R times the sum of lambda I squared. Okay, so that's the obvious Cauchy-Schwarz, but R is what we want a lower bound of. And it's sort of amazing that this argument is going to work, because R and N are not going to be that different. But anyway, that's exactly what works. This argument is, I think, was discovered in several different places. There's a paper of Alon which does much more sophisticated things, but that's like the starting point, this argument. So anyway, so you do this Cauchy-Schwarz, and now you go back from the spectral decomposition. Sum of the eigenvalue squared is just the Frobenius norm of the matrix. It's just the sum of the squares of the entries. So this is R times the sum of the I and j, Aij squared. And this we know again. We look here and we get R times the squares of the diagonal entries are k squared. So we get here k squared times n. And the off diagonals, we get at most t squared in every entry. So we get at most n squared t squared. OK, so we have this left-hand side and this right-hand side, and I'll spare you the little algebra to say that this implies that R is at least n minus nt over k squared. Okay, so this in the very simple case that the matrix is 0, 1, you get it. You get, in fact, something even stronger than what I promised you. The Q does not appear in this argument at all. Okay. Okay, that's good. So what are we going to do? It's clear? Okay, so but this is obviously a completely uninteresting case, right? I mean, why should the entries of M be 0, 1? We are supposed to take care of the general case where they are arbitrary. So let's do the general case.
Is this loss of 1 over k squared tight? So here you're losing nt over k squared.
No, it's not tight, because I mentioned that Shubhangi...
But that was for the original problem, so does it apply to even this?
It applies to even this, yeah. That's exactly where it applies to. There's another Cauchy-Schwarz hiding that you can add, and which will save you this square. So M was a general matrix. All we knew that it has many non-zeros and in the columns, few non-zeros in the rows, and small intersections. And if we look at this argument that we used here about the matrix A, we really, we use just these two conditions. And, AII, if we call this, if we call the columns, I know, M1, M2, Mn, the columns of M, then AII was just the inner product of Mi, namely just the norm squared of this column. And Aij was just the inner product of Mi and Mj. Well, if we could arrange that these guys are big and these guys are small, then we can do the same analysis. But how can we arrange it? Of course, it's not true initially. So the point is, the next really important observation is that we are not going to change. We are out to prove a rank lower bound on M. The lower bound, the rank of M is not going to change if we multiply every row by a constant or every column by a constant. right? I mean, it's just we are free. No, different constants. So here is our matrix M, and we will multiply, this column by some constant alpha 1, this column by some constant alpha 2, this column by some constant alpha n. Just multiply it by some arbitrary constant, and this by beta 1, beta m. I don't know how many rows here. L. So if we multiply, this is called scaling. So multiplying rows and columns by constants, which is called scaling, non-zero, of course, by non-zero constants, otherwise, does not affect the rank. So we can do it. And what the remaining lemma that we have to prove is that there exist constants alpha 1, alpha n, and beta 1, beta L, whatever we need, such that, when you look at, so let's call, after the multiplication, let's say the scaling converts M to M tilde. Okay, so we get a new matrix after we multiply this. So that in M tilde, what we have is what we want. Basically, that the M tilde I, M tilde J is at most T, the same T. And so exactly what we want here. So, and the M tilde I squares is for every I, not. And for every I, M tilde I is at least, well, we wanted K and had K in the thing before. Well, we may lose this Q factor. Q was this constant 3. That, what?
The diagonal values are they the same?
So there will be at least K of
No
us.
longer the same, no longer the same.
No, not long, but this is like 2 or 3 or something. 3. Okay. Okay, so this lemma requires some information about scaling, which I'm going to take the rest of the 10 minutes I have to tell you about matrix scaling. And I'm not going to prove this lemma. I'm going to tell you about the original scaling problem and its solution by Sinkhorn. I'll just mention that to do this, you need some generalization. In particular, we are working here in L2 and initial scaling. So here we do it in L2, so Sinkhorn. We're going to use Sinkhorn scaling. So the initial Sinkhorn scaling works in L1, but that's not a big deal. We just more or less square the entries here and work in L1. And the original scaling here works in the square case, but that's very easy. So we are in some rectangular matrix, but that's not a big deal. Rectangular matrix. And the most important thing is really under what condition the scaling I'm going to talk about works. And you have to import this here, and that's the reason you lose a factor Q. But let me just forget about this lemma. It can be done with the tool that I think you should know about and is really cool, which is matrix scaling. So what is the original matrix scaling problem? Yeah, exactly. We will need to modify M so that these conditions hold, and that's where we lose another Q factor, which is not significant. Yes. But just this scaling thing is really cool. So what was the origin? So this is Sinkhorn in 64. Look at the following problem. I give you some matrix. Let's give it a different name, B. B non-negative. So all the entries of B are non-negative. Okay? Maybe 0, but non-negative. Let's say n by n matrix. And what you want to do is to scale it. So again, multiply it by alpha 1 up to alpha n and beta 1, beta n, non-zero, maybe actually positive constant, so that it moves into a matrix B tilde. And what you want B tilde to have, the property you want to have it, is that B tilde is doubly stochastic. Doubly stochastic means that row sums and column sums are all 1. Okay? That's what you want to do. You can't always do it. Can you give me an example?
Non-negative answers, right? And B tilde.
So you multiply, so all the alpha i's and beta j's are positive. So suddenly, if this was non-negative, this was it will be non-negative. And that's what you want. So the question is, under which conditions can you achieve it? Excuse me? Yeah, it's a square matrix, yes. It's a square. It's an n by n matrix.
So you can't do this for like 1, 1, 0, 1, right?
Well, there is a simpler example with.
Partition it then, like blocks.
Okay. Certainly, let me give you one example where you cannot do it. So let's look at examples for. You cannot do this. You cannot make this doubly stochastic. Okay, 0 matrix is impossible. Now, somebody gave here a very good example. This matrix. If you want to scale this matrix, you want row sums and column sums to be 1. Then whatever I multiply, if I multiply this, this has to be 1 over, then this has to be 1 over alpha, right? Because at the end, this has to be 1 because of this row sum. 0 will never become non-zero. So in fact, scaling preserves a 0 non-zero structure. So this has to be like that. Similarly, if this is beta, this has to be 1 over beta because of this current sum, right? So you can see that scaling will never eliminate this completely. So this calls for slightly revising the idea of making a matrix doubly stochastic. You want it to make almost doubly stochastic, which means that what you want is that row sums minus 1 and column sums minus 1 can be made smaller than epsilon for every epsilon. So again, scaling is good if for every epsilon that you give me, every proximity that you give me, I can find some scaling factors that will make all the row sums and all the column sums 1 to within epsilon. Okay, so that's what we want to do, and suddenly now this can be done, right? Because I can make this as small as I want. Sorry.
You have a perfect match.
Yes. So the question is, under which conditions it can be done, and what Latsi said is that, so we want to make B almost doubly stochastic, and the theorem, Sinkhorn's theorem, is that this can be done, scaling, doubly stochastic scaling exists, if and only if B, the matrix you are given, has a perfect matching. So let me write it in a different way. The permanent of B is positive. So the permanent of B, I remind you, is this sister of the determinant function. It's just a sum over all permutations in Sn. The product I goes from 1 to n, bi sigma of I. So it's like determinant without the signs. And it's positive exactly if there is some non-zero diagonal in this matrix. Now, so I'll just conclude this story with the proof of this really amazingly cool theorem.
So is there a relationship between the bound permanent and the epsilon?
What?
Is there a relationship between the bound permanent and the epsilon? What is it?
No, so no. Remember that, so the quantifiers here that, yeah, that you want that no matter what epsilon, you can find such coefficients. Here, there is no bound on the, this can be done. Side of the coefficients will depend on epsilon. There is a paper that I wrote some 10 years ago with some Ornitsky and Lineal, where there are basically strongly polynomial algorithms to find a scaling. So it does not depend on the the size of the entries, and the running time does not depend on the. But let me not go there. I just want to prove to you this this result. The fact that there's a one direction which is simple, that if there's no perfect matching, then you cannot come to a scaling. But it's not difficult. I want to prove to you the other direction, that if there is a perfect matching somewhere, if the permanent is strictly positive, then you can find a scaling. So how do you find a scaling? The idea is really beautiful, sort of hard to believe that it would work. And it says the following. You have a matrix, non-negative matrix, and you want to make all the row sums and all the column sums 1, or approaching 1. So what can you do? Here's the matrix B. Well, you look at the first row sum. It's some row sum R1. You want the row sum to be 1. So you can scale. You can divide by 1 over R1, right? If you just multiply this row by this constant, 1 over the row sum, then this row sum will become 1. You can multiply the second by 1 over the row sum. You'll get 1 here. 1 over Rn. So you can definitely make all the row sums 1 really easily. That's half the problem. Right? All we need to do is the columns. The column sums we don't know anything about. But we can look at them and look at, well, the first column sum is maybe S1. So let me multiply this by 1 over S1. Let me multiply this by 1 over this column sum, 1 over S2. Okay, that's good. So I made all the column sums 1. What's the problem? Well, of course, I ruined the row sums. But I can fix them. Maybe now the row sum is R1 prime. Let me divide by R1 prime. Let me divide this by R2 prime, and so on. Let me fix the rows again. So now I can fix the rows again. But of course, I ruined the columns. But I can fix them, right? Or I can. OK, so you understand at least that I'm describing some process, right? And the theorem is that this process converges. Now, why does it converge? I mean, if you see any proof of convergence, right? So I claim that if the permanent is positive, then this thing converges to a doubly stochastic matrix. Okay. Now, why should this be true? Any convergence proof must have some Lyapunov function, right? Something that improves. What do you think improves in this process? No? Okay. The function which improves is written on the board. Yes, a permanent. So let's just see, it's a one-line argument, and this will be the end. So let's say that we have a matrix B, and we already have, let's say, the column sums are 1, and now we are multiplying this by 1 over R1, 1 over Rn. We want to say, and this sends us to another matrix, let's say B prime. And this is the thing we iterate, right? So what happens in this step? Let's look at the permanent of B prime. Well, the nice thing about scaling is that its effect on the permanent is clear. Its effect on the permanent or the determinant, anything that depends just on one row, one entry from each row and one entry from each column is predictable, right? So it just changes. It will be just 1 over R1 times 1 over R2, 1 over Rn times the permanent of B, right? Good. Now, which inequality should we use now? Not Cauchy-Schwarz. We have a product. Very good. No, well, I mean, you can call it that, but it's, yeah. So if we use the arithmetic geometric mean, we get here. Okay, so we use the inequality we know, and we got this. Now, what do we know about what's written here? What is the sum of the row sums? The sum of the row sums is the sum of the entries in the matrix. So it's the sum of the column sums also. But the sum of the column sums is n. So this thing is 1. We are almost done. This just says that the permanent does not decrease. But actually, you know that the arithmetic geometric inequality is tight only in one case, when all the numbers are equal. If all the numbers were equal, we'd be done. So, in fact, if the numbers are sort of epsilon far from equal, there'll be a strict inequality here, and we can actually multiply by some, if the vector r minus 1 was bigger than some epsilon in any norm you want, we could put a little plus something that depending on epsilon, namely there'll be an increase. So it really actually strictly increases if there was a gap. So we are always making progress. On the other hand, we cannot make progress for too long, right? What do we know about the permanent of a matrix? The permanent of a matrix is at most the product of the row sums, or at most the product of the column sums. So we know that all these matrices in the sequence, they are all bounded by 1, and we are increasing noticeably as long as we are far from our target, so we are convergent. That's it. Thank you.